Welcome to this tranquil exploration of big data. As you settle into a comfortable space, allowing your breath to deepen and your body to relax, we will embark on a gentle journey through the fundamental concepts that help us understand the vast and intricate world of information. Let your mind drift softly, absorbing these ideas at a slow and peaceful pace, knowing that each word is designed to guide you into a state of calm learning and restful sleep. We will begin by gently observing how data can be presented, moving through various ways to visualize its quiet stories. Then, we will slowly unfold the methods used to predict patterns and make sense of complex relationships, always with a soothing rhythm. We will discover the hidden dimensions within our data and explore the gentle processes of learning from information, step by careful step. Allow the steady flow of these thoughts to wash over you, calming your mind as you gradually drift into a deep and restorative slumber. Our journey begins with the serene art of visualizing data. We first consider what is known as univariate data. This refers to data that consists of observations on only a single variable or a single feature. When we look at univariate data, our quiet focus is on analyzing this one variable in isolation, without considering its connections or relationships with any other variables. Imagine, for example, observing the heights of students in a class. We might have a list of numbers: 150 centimeters, 160 centimeters, 170 centimeters, 165 centimeters. This is univariate because we are looking at only one aspect, the height itself. Similarly, consider the daily temperatures recorded in a city: 20 degrees Celsius, 22 degrees Celsius, 19 degrees Celsius, 21 degrees Celsius. Again, this is univariate, as we are observing just one variable, the temperature, in its simple form. The main, peaceful goal when working with univariate data is to quietly examine the data's distribution. We want to understand several calm aspects of this distribution. First, we look at central tendency. This tells us where the middle or typical value of the data quietly resides. Common measures of central tendency include the mean, the median, and the mode. The mean is the simple average, a familiar concept. The median is the middle value when all the data points are arranged in order, a point of balance. The mode is the value that appears most frequently, a quiet peak in the data. Second, we consider dispersion. This describes how spread out or scattered the data points are. Measures of dispersion include the range, which is the difference between the highest and lowest values, the variance, which quantifies the average of the squared differences from the mean, and the standard deviation, which is the square root of the variance, providing a more interpretable measure of spread. Third, we engage in visualization itself. This involves creating gentle pictures of the data, such as histograms and box plots, to visually perceive its quiet shape and characteristics. Let's gently explore box plots, a serene way to visualize univariate data. A box plot provides a clear, concise summary of the data's distribution. It quietly displays the median, quartiles, and potential outliers. Imagine a calm box. The central line within this box represents the median, the middle value of your data, softly dividing it into two halves. The edges of the box itself indicate the first quartile, or Q1, and the third quartile, or Q3. The first quartile marks the 25th percentile, meaning 25% of the data falls below this point. The third quartile marks the 75th percentile, with 75% of the data falling below it. The length of the box, from Q1 to Q3, represents the interquartile range, or IQR. This range quietly encompasses the middle 50% of your data. From the box, slender lines, called whiskers, gently extend outwards. These whiskers stretch from the edges of the box to the smallest and largest values within a certain range, specifically 1.5 times the interquartile range. Any data points that fall beyond the quiet reach of these whiskers are considered potential outliers, unusual observations that stand apart from the main body of the data. Let's delve a little deeper into the gentle interpretation of a box plot. The length of the box itself is a quiet indicator. A wider box suggests more variability in the middle 50% of the data, meaning these values are more spread out. A narrower box implies less variability, with the central data points clustered more closely together. the position of the median within the box tells us about symmetry. If the median line is perfectly centered within the box, it quietly suggests that the data is fairly symmetric, meaning the distribution is roughly balanced on both sides of the median. However, if the median is closer to either Q1 or Q3, it indicates skewness. If it leans towards Q1, the data might be skewed positively, with a longer tail extending towards higher values. If it leans towards Q3, it might be negatively skewed, with a longer tail towards lower values. The lengths of the whiskers also offer calm insights into symmetry. Equal whiskers on both sides suggest symmetric data, a peaceful balance. Uneven whiskers, on the other hand, imply skewness. A longer whisker suggests more spread in that particular direction, a gentle stretching of the data. An ideal box plot, a picture of quiet harmony, would exhibit specific characteristics. It would have fewer outliers, or ideally, none at all, indicating a dataset without extreme values that stand too far apart. It would also display no extreme skewness, suggesting a balanced distribution. Furthermore, an ideal box plot would show high symmetry, both for the median being centered within the box and for the whiskers being of similar length. This high symmetry often indicates a normal or bell-shaped distribution, a common and often desired pattern in data. Finally, the box itself should not be too narrow, as this would suggest very little variance in the middle 50% of the data, perhaps indicating a lack of meaningful spread. Conversely, it should not be too wide, which would suggest an extremely high spread or variability, potentially making patterns harder to discern. A well-proportioned box quietly tells a clear story. Moving to another type of univariate data, we calmly observe time series data. Time series data is a sequence of observations taken over time, at regular or irregular intervals. When visualizing time series data, we often look for several gentle patterns. These include irregular fluctuations, which are unpredictable, short-term movements that don't follow a clear pattern. There are also cyclical patterns, longer-term oscillations around a trend, often influenced by economic cycles that may last for several years. We look for a peaceful trend, a general upward or downward movement that persists over a long period, indicating the overall direction of the data. And finally, seasonal patterns, which are regular, repeating fluctuations that occur within a fixed period, like daily, weekly, monthly, or yearly, reflecting recurring events or conditions. When displaying time series data with multiple lines, certain gentle guidelines help maintain clarity. Ideally, the lines representing different series should not cross frequently, as this can make it difficult to follow individual trends. Sometimes, separate axes may be required for different series if their scales are vastly different, ensuring each trend is clearly visible without one dominating the other. At other times, having the same scaling for multiple lines can be beneficial, as it helps emphasize differences in performance or magnitude across the series, offering a quiet comparison. We must always be aware of axis spacing, ensuring that the intervals are clear and the visual representation accurately reflects the underlying data. Next, we gently consider bar plots for univariate data. Bar plots are primarily used for categorical data, where data points fall into distinct categories rather than continuous numerical values. They are particularly well suited for displaying the frequency or proportion of observations within each category. Bar plots are best when you have many categories, allowing for a clear visual comparison of each group. In such cases, the order of the categories on the axis often does not inherently matter, though arranging them alphabetically or by value can sometimes add clarity. These plots quietly help us differentiate strengths and weaknesses among categories, making it easy to see which groups are more prominent or less so. A histogram is another soothing visualization for univariate data. Unlike bar plots for categorical data, histograms are used to show the distribution of a continuous variable. They do this by grouping the data into distinct ranges called bins. When you use a histogram, you want to see the overall shape of the data, whether it's normal, skewed in one direction or another, or perhaps uniformly distributed. Histograms are great for this purpose, providing a peaceful visual summary of where data points are concentrated and how they spread out. Why are they so useful? They help visualize frequency distributions, allowing you to quickly spot if the data has one peak, unimodal, or two peaks, bimodal, or if it follows a gentle normal distribution, which often looks like a bell curve. For example, a histogram could show the distribution of students' test scores, revealing if scores cluster around the average or if there are two distinct groups of high and low scores. It could also analyze the speeds of pitches thrown in a baseball game, showing the frequency of different speeds. Now, we quietly transition to the scatter plot, a visualization often used for multivariate data, though it can show relationships between two continuous variables. When to use a scatter plot? You want to use it when you wish to show the Serene relationship between two continuous variables. It is great for detecting correlation or patterns in paired data. For instance, if you plot height on one axis and weight on another, you might observe a positive correlation, where taller individuals tend to be heavier. Why is a scatter plot useful? It is a peaceful tool for identifying trends, clusters, or outliers in bivariate data. Trends can be linear, where points follow a straight line, or non-linear, where they follow a curve. Clusters might reveal groups of data points that are similar to each other, while outliers are points that lie far away from the main pattern. Scatter plots help us spot these linear or non-linear relationships with gentle ease. Examples include plotting player height versus weight on a sports team or examining the relationship between training hours and performance scores. The pie chart offers a calm view of proportions. You use a pie chart when you want to show proportions or percentages of a whole. Each slice of the pie quietly represents a category's share of the total. Pie charts are best for datasets with a small number of categories, ideally 3 to 5 segments, as too many slices can make the chart cluttered and difficult to read. Why is it useful? It helps visualize how parts contribute to a whole, providing a serene overview of the breakdown. However, it can be hard to read with too many slices or when there are only small differences between segments. For example, a pie chart could display the percentage of goals scored by each player on a soccer team or show the market share of different sports equipment brands. The time series plot, which we touched upon earlier, is a valuable tool for univariate data that changes over time. You use a time series plot when you want to show how a variable changes across dates, months, years, or any other time unit. It is commonly used for tracking trends or seasonal patterns. Why is it useful? It excels at spotting trends, cycles, and patterns over time, revealing the quiet rhythm of the data. It is also great for showing before and after effects of events, such as rule changes in sports, by clearly illustrating how the variable's behavior alters following a specific point in time. Examples include tracking a team's winning percentage over a season or monitoring heart rate changes over time during a workout. Finally, another type of bar plot, distinct from the categorical one, is used to compare quantities across categories. You use this bar plot when you want to compare numerical quantities across different categories. It works well for both counts, or frequencies, and values, such as averages or sums. This type of bar plot is best for comparing discrete categories or group data, offering a clear side-by-side view. For categories with long names, using horizontal bars can be more effective, as it allows the labels to be read easily without overlapping. Examples include comparing the number of goals scored by different soccer players or showing the average reaction time of athletes in different sports. To summarize these Serene visualization tools, a box plot is used for distribution and outliers, best at showing spread, quartiles, and outliers, like salaries by department. A histogram is for continuous variable distribution, best at showing the shape of data, like test score distribution. A scatter plot shows relationships between two variables, best at showing correlations and patterns, like height versus weight. A pie chart is for proportions of a whole, best at showing part-to-whole relationships, like goals per player in a season. A time series plot shows change over time, best at showing trends, cycles, and patterns, like winning percentage over a season. A bar plot is for comparing categories, best at showing counts of values by group, like goals scored by each player in a game. Now, we gently move to our second calm topic, regression. Regression is the peaceful act of creating a mathematical model. This model is intended to predict an output value from a specific input, always assuming a gentle causal relationship exists and that we have a known structure for our model. Let's begin with the derivation of linear least squares regression. In its introduction, simple linear regression quietly predicts a change in an output variable, typically denoted as y, based on a change in an input variable, often called x. This method gently enables us to investigate how changes in the response variable, also known as the outcome or dependent variable, correspond to a given change in the explanatory variable, which is the predictor or independent variable. Suppose we have some known input data. You possess a set of peaceful data points, each consisting of an x value and a corresponding y value. We can represent these as pairs x1, y1, x2, y2, and so on, up to xn, yn. From this known input data, we aim to derive a predicted output. This predicted output, denoted as y_hat, will approximate these actual data points by fitting a straight line to them. This line takes the simple form of y_hat equals y_1 times x plus y_0. Here, y_hat is our predicted output, and the x is our input value. Our calm goal in this process is to find the optimal coefficients a_1 and a_0 that define this best fit line. The core objective of regression is to peacefully minimize the total error. First, we must quantify this error. The error, often denoted by the Greek letter epsilon, represents the difference between the model's prediction of the output, y_hat, and the real, observed data point y. Imagine the gentle distance between your predicted line and the actual point. To explain all the variability present in a dataset, we use several measures, all derived from the concept of squared errors. The total sum of squares, or SST, measures the total variability in the dependent variables y. It's calculated by summing the squared differences between each observed y value and the mean of all y values. Think of it as the total spread of our data points around their average. Then, there's the regression sum of squares, or SSR. This measures the variability in y that is captured or explained by our regression model. It's the sum of the squared differences between each predicted y_hat value and the mean of y. This term quietly tells us how much of the original spread our model has successfully accounted for. Finally, and most crucially for our objective, we have the residual sum of squares, or SSE, also known as the sum of squared errors. This measures the variability in y that is not explained by our model. It is the sum of the squared differences between each observed y value and its corresponding predicted y_hat value. This is the error we are striving to minimize. The least squares approach is a peaceful method for achieving our objective. Since the function representing the total error of the model, specifically the sum of squared errors, or SSE, is convex, we can calmly seek its global minimum. A convex function has a gentle, bowl-like shape, meaning there's only one lowest point, which makes it easier to find. We express the total error of the model as the sum of squared errors. The formula for SSE involves summing up the squared differences between each observed value, y_i, and its corresponding model predicted value, y_hat x_i. Here, y_i is the actual, observed value from our data, and y_hat x_i is the value our model predicts for the given input x_i. Since our model is a linear equation, y_hat equals y_0 plus y_1 times x, we get an unconstrained optimization formula, minimize SSE, which is the sum of the squared differences between a_0 plus y_1 times x_i and y_i. We can visualize SSE as a gentle function of our decision variables, a_0 and a_1, often represented on contours or surfaces, guiding us towards that lowest, most peaceful point. To solve this analytically, we use principles of calculus to find the global minimum of the SSE function. The process involves three calm steps. First, we take the partial derivative of SSE with respect to one unknown coefficient, a_0. This means we treat a_1 as a constant and differentiate with respect to a_0. Second, we take the partial derivative of SSE with respect to the second unknown coefficient, a_1. Here, we treat a_0 as a constant and differentiate with respect to a_1. Third, we set each of these partial derivatives to 0. This is because at the minimum point of a continuous function, the slope, or derivative, is 0. By setting both partial derivatives to 0, we create a system of equations that we can then calmly solve for our two unknown parameters, a_0 and th_1. As an example, to minimize SSE, we take these partial derivatives with respect to a_0 and y_1, set them to 0, and gently solve for the coefficients. This leads us to a system of normal equations. These equations, derived from our partial derivatives, can be expressed in a concise matrix form. This matrix form provides a structured way to solve for the unknown coefficients a_0 and a_1, allowing us to find the line that most peacefully fits our data. Let's walk through a peaceful example of a linear regression problem. Suppose we have 4 data points, 1, 2, 2, 3, 3, 5, and 4, 7. Our calm objective is to fit a line to these points that minimizes the sum of squared errors, following the forms and y_hat equals a_1 times x plus a_0. First, we gently compute the required summations. We find n, the number of data points, which is 4. We sum all the x_ia values, getting 1 plus 2 plus 3 plus 4, which equals 10. We then sum the squared x_ia values, 1 squared plus 2 squared plus 3 squared plus 4 squared, which gives 30. Next, we sum all the y_ia values, 2 plus 3 plus 5 plus 7, resulting in 17. Finally, we compute the sum of x_i times y_ir for each point, 1 times 2 plus 2 times 3 plus 3 times 5 plus 4 times 7, which equals 51. Second, we solve for the partial derivatives and plug in these summations. This gives us two peaceful equations. For the derivative with respect to a_0, we get 4 times a_0 plus 10 times a_1 equals 17. For the derivative with respect to a_1, we get 10 times a_0 plus 30 times a_1 equals 51. Third, we calmly solve this system of equations for a_0 and th_1. We can express a_0 in terms of a_1 from the first equation, a_0 equals 17 minus 10 times a_1 divided by 4. Substituting this into the second equation and gently solving for a_1, we find that th_1 equals 1.7. Plugging this value back into our expression for a_0, we discover that a_0 equals 0. So, our peaceful regression line is y_hat equals 1.7 times x. Alternatively, we could solve this system using matrices. We form a left matrix M containing our summations, a middle column vector for our unknowns a_0 and a_1, and a right column vector for our y summations. Solving this matrix equation also peacefully yields a_0 equals 0 and a_1 equals 1.7. The results of our linear regression suggest a direct, positive linear relationship between x and y in this dataset, a quiet insight into their connection. Now, let's gently progress to polynomial regression. In the introduction, what we call linear regression is considered linear in the parameters. This means that our coefficients a_0 and a_1 are combined in a simple, linear way, weighed by other terms. Polynomial regression can be thought of as a calm extension of this concept. It introduces polynomial terms, such as x squared, x cubed, and so on, to capture non-linear relationships within the data. Instead of simply fitting a straight line, polynomial regression quietly fits a curve with higher-order terms. For example, a polynomial model of order n might take the forms y_hat equals a_0 plus th_1 times x plus th_2 times x squared, all the way up to n times x to the power of n. This allows our model to gently bend and adapt to more complex patterns in the data than a straight line could capture. The sum of squared errors, or SSE, for polynomials naturally extends this idea. The formula for SSE for polynomial regression encompasses these higher-order terms. It involves summing the squared differences between the observed y values and the predicted y_hat values, where y_hat now includes the polynomial terms. Just as with simple linear regression, we would take partial derivatives of this polynomial SSE with respect to each coefficient, from a_0 to all the way to say_n. Setting these partial derivatives to 0 would then allow us to solve for the optimal coefficients that minimize the error for our polynomial curve. This system of normal equations, again, can be expressed in a quiet polynomial matrix form, providing a structured approach to solving for these coefficients. Next, we calmly delve into the analysis and application of regression, focusing on fit metrics, testing, and training strategies. To assess the goodness of fit of our model, we use metrics like R². The coefficient of determination, R², is a peaceful measure that tells us the proportion of the variance in the dependent variable that is explained by the independent variables, as predicted by our model. The formula for R² is 1 minus the ratio of the sum of squared errors, or SSE, to the total sum of squares, or SST. The numerator, SSE, is essentially the measure of leftover variance, or the error that remains unexplained by our model. The denominator, SST, represents the total variance in the dependent variable. R² values range from 0 to 1. An R² of 0 is the lowest possible value. It essentially means that our model is no better than simply estimating the entire data set with just the mean of y. An R² of 1, on the other hand, implies that the independent variable x explains everything in a y, indicating a perfect one-to-one correlation between the x values and the y response, a state of quiet harmony. However, a high R² does not always peacefully mean that we have a well-fit model. Adding more terms to our polynomial regression, for instance, is guaranteed to increase the R² value, even if those terms don't truly improve the model's predictive power. If the data contains any sort of noise or random fluctuations, simply adding more terms can lead to overfitting the model. Overfitting means our model becomes too specific to the training data, memorizing its noise and peculiarities rather than learning generalizable patterns. This can cause spurious, or false, and random results when the model is applied to new, unseen data. In real-world applications, models can be quite complex, and R² is often just a gentle guide, not the sole indicator of model quality. Visualization alone might not always give enough insight into the model's true performance. Therefore, a systematic approach is required to properly evaluate how well our model performs, beyond just looking at a single number. This brings us to the crucial aspect of a testing versus training strategy. In training, we typically use 75 to 80% of our data to train the model. This means we feed this portion of the data to the algorithm so it can learn the relationships and predict the model coefficients. The R² value calculated on this training set is often denoted as R²_TR. Conversely, in testing, we use the remaining 20 to 25% of the data to test our trained model. Here, we attempt to predict the values for this unseen data. The R² value calculated on this testing set is denoted as R²_TE. Our goal is that if R²_TR and R²_TE are similar, meaning the difference between them is smaller than a chosen error tolerance, then the model is considered not biased or overfit. We want the prediction accuracy and reliability to be roughly the same for both training and testing data, indicating that the model generalizes well to new information. If we have a multidimensional, big N data set, a careful validation process is needed. We might pick a univariate case, using one variable at a time, and a small sample size, for example, 25% of the data, to ensure the model generalizes well and avoids overfitting. The validation process typically involves proposing a model on a small dataset, then training the model on the larger dataset, and finally testing the model on the smaller dataset to check its performance on unseen data. Consider a calm chat example. Suppose we have 100 data points where we want to predict house prices based on square footage, using a simple linear regression model. First, we split the data into an 80% training set and a 20% testing set. We fit the simple linear regression model on the training set, and after training, we calculate an R²_TR of 0.92. This means 92% of the variance in house prices is explained by square footage within the training data. Then, we apply this trained model to the test set and compute an R²_TE of 0.85. This means 85% of the variance in house prices is explained by square footage in the test data. Now, we compare r²_TR and r²_TE. If our error tolerance is 0.1, and the absolute difference between 0.92 and 0.85 is 0.07, which is less than 0.1, then our model generalizes well and is not overfitting. However, if our model were overfit, it would perform very well on the training data but poorly on the test data. This indicates that the model has memorized the training data instead of learning generalizable patterns. A good model quietly shows similar r² values for training and testing. An overfit model would have a significantly higher r²_TR than r²_TE, a clear sign of memorization. An underfit model, on the other hand, would show low r² values for both training and testing, indicating it hasn't captured enough of the underlying patterns. It's important to remember that beyond a certain point, r² on the training data will show diminishing gains as the r² for the test data gets worse, a gentle reminder of the dangers of overfitting. Now we softly transition to basis function regression. In this calm approach, we can handle any function, as long as our model remains linear with respect to its coefficients, that are our values. Basis function regression is a method where we gently transform the input variables using a special set of functions, called basis functions. This transformation allows us to capture complex, non-linear relationships within the data that simple linear models might miss. Instead of fitting a simple linear model directly to the raw input variables, we first quietly map these variables to a higher dimensional space. Once in this new space, we then apply regression, which becomes a linear combination of these basis functions. When we consider our predicted output, y_hat, as an arbitrary function of x, it can be expressed as a peaceful sum. y_hat equals the sum of a_m times f_m x, where m ranges from 1 to sem. In this formulation, there is no a_0 intercept term explicitly stated, meaning the model passes through the origin or its intercept is absorbed within the basis functions. Each f_m x is a distinct function of the independent data x, representing a different gentle transformation. M simply denotes the total number of functions or terms we are including in our basis. Examples of valid basis functions include combinations like a_1 times usin x plus a_2 times tan_inverse x. These are perfectly acceptable as long as we combine them linearly. This means the coefficients a_1 and a_2 remain simple multipliers. However, we cannot have non-linear coefficients. Invalid examples would include expressions like a_1 times usin a_2 times x, or 1 divided by a plus x. The key here is that the coefficients must remain outside of the function itself. If they become embedded within the function, it complicates the derivatives, making it impossible to solve for the coefficients using our standard algebraic matrix methods. The polynomial sum of squared errors, or SSE, for basis functions naturally extends the concept of minimizing error. It is the sum of the squared differences between the observed y values and the predicted y_hat values, where y_hat is now expressed as the sum of a_m times f_m x for each data point. To find the coefficients that minimize this SSE, we calmly take partial derivatives of the SSE with respect to each coefficient, for example, a_1. This involves differentiating the squared error term and applying the chain rule, much like we did for polynomial regression. Setting these partial derivatives to 0 yields a system of linear equations, which can then be solved. Just as before, this system of normal equations can be expressed in a structured basis regression matrix form, providing a clear and organized way to solve for all our coefficients. In a Serene basis function lecture example, we might encounter various features that can serve as basis functions. These could include a sin x, which captures oscillating relationships, e to the power of negative x, useful for representing a large drop in y values or a peaceful tail in the data, x itself, which accounts for a potential linear relationship, and ln x, which can describe exponential decay. Other functions, such as polynomials and rational functions, are also quietly considered. The choice of basis functions depends on the underlying patterns we expect to find in the data. Setting up the SSE linearly with these basis functions and then translating it into a matrix system allows us to solve for the coefficients, as demonstrated earlier. This matrix, often referred to as a matrix A, helps us find the coefficients x, which are our values, that lead to the solution b, our summations involving y and the basis functions. This approach extends calmly to dimensions greater than 1. It is possible to achieve any type of regression, whether linear, polynomial, or basis function, in multiple dimensions. The underlying mathematics does not significantly change, though the computational costs may increase. However, with modern computing power, this is usually acceptable. When we consider visualization in this multidimensional context, instead of having a single input variable, x, we now have a vector x with multiple dimensions, such as x_1, x_2, and so on. Similarly, the output y can also have multiple dimensions in some cases. If we suppose x is a two-dimensional input, say, x_1, x_2, transposed, our model then tries to fit to a surface in 3 dimensions instead of a simple line in 2 dimensions. We want our regression functions, f_m, to peacefully incorporate relationships between the outputs y_ij for some input vector, x_ij. Any basis function, f_m, could potentially contain or omit elements from the input vector, x, allowing for flexibility in how it captures these relationships. When performing basis regression, it is important to consider all possible input feature combinations, even if some basis functions don't explicitly use them. The input xk can be thought of as a matrix x_1, x_k, where k is the number of columns or features. The visualization of a surface fit helps us understand this concept. Imagine a peaceful surface gently fit to the data points, chosen to minimize the sum of squared errors. The individual dots on this plot represent our real, observed data. The color gradient sheet on the surface represents the predicted values of the dependent variable, quietly showing how our model interpolates and extrapolates across the input space. The predicted output is displayed on the y-axis. With 2 independent variables on the x and a z-axis, the third dimension is represented by different sheets, where each sheet corresponds to a fixed value of one of the input variables, offering a tranquil cross-section of our fitted surface. Now, we gently turn our attention to the next units of our learning journey, starting with latent variable methods. Latent variable methods are calm techniques designed to reduce the dimensionality of data while carefully preserving as much relevant information as possible. They achieve this by quietly finding a new set of orthogonal axes, which we call hyperplanes, that best explain the variance present in the data. Imagine distilling the complex essence of your data into simpler, more fundamental components. In the context of linear regression in multiple dimensions, we are essentially looking for the coefficients of these hyperplanes. This means that methods like principal component analysis, or PCA, and partial least squares, or PLS, are deeply rooted in linear regression, building upon its principles to extract meaningful hidden structures from our data. Next, we gently touch upon artificial neural networks, or ANNs. An artificial neural network is a computational model peacefully inspired by the structure and function of biological neural networks, much like the human brain. It consists of layers of interconnected processing units called neurons or nodes. These neurons process data through weighted connections, where each connection has an associated weight that determines the strength and influence of the signal passing through it. ANNs typically have an input layer, which receives the initial data, one or more hidden layers, where the computational processing occurs, and an output layer, which produces the final prediction or classification. The ANN method is fundamentally about finding the optimal weights, or coefficients, that combine linear, nonlinear, and bias terms, which are additional factors, across one or more layers. While deeply rooted in basis function regression, traditional sum of squared errors techniques cannot be directly applied here in the same way because the outputs of one layer feed into the next, meaning subsequent weights and coefficients non-linearly depend on previous weights. Therefore, training an ANN quietly requires an iterative procedure, gradually adjusting weights to minimize error over many cycles. Let us now calmly delve into topic 3, latent variables. The definition of a latent variable is simply any variable that is not directly observed. think of it as a hidden influence or an underlying concept. For example, your overall health is a latent variable. Your doctor doesn't measure your health directly. Instead, they measure various observable indicators like your weight, your blood pressure, your cholesterol levels, and other physical attributes. These observable measurements are used to infer your underlying state of health. Latent variables possess several calm characteristics. They have the same number of observations, or rows, as the original, larger dataset, meaning they represent each individual case. However, they aim to represent these observations with a smaller number of components, often denoted as a, where a is much less than k, the original number of variables. These components represent a score for each observation on the latent variable. Basically, latent variables act as peaceful factors that can represent a larger group of correlated variables, simplifying our understanding of the data. Their most important role is that they explain the most variance in the observed data, quietly capturing the dominant patterns and trends. For example, imagine measuring the temperature in a room at several points over time. We might have data from the front left, front right, back left, and back right corners. Each corner's temperature over time would be an observed variable. A latent variable might emerge that represents the overall room temperature. While we don't directly measure overall room temperature, it influences the readings at each corner. Visualizations can show how these individual temperature lines might correlate or diverge. If we plot temperatures from, say, the front left versus the back left, we might see a clear positive correlation, indicating they tend to rise and fall together. If there were no variance with these points, they would all cluster together, perhaps around a central point, showing no relationship. A little bit about principal component analysis, or PCA. For a Serene frame of reference, instead of doing regression to see how one output is based on one variable, we now have multiple variables. Our goal is to see how they quietly correlate to each other and to gather a summary for the dataset using the fewest number of descriptors. These descriptors are often referred to as summary variables or scores. There's a quick, gentle differentiation between PCA and latent variables, although their concepts are related. A latent variable is a hypothetical construct or factor that is not directly observable but is inferred from observed variables. Examples in psychology include intelligence, personality traits, or depression. Latent variable models help us understand the underlying structure of data, offering peaceful insights into complex phenomena. In contrast, a component in PCA refers to a new, uncorrelated variable derived from a set of original, potentially correlated variables. These components are linear combinations of the original variables and are ordered by the amount of variance they explain. PCA is a data reduction technique, meaning its calm aim is to reduce the number of variables while retaining as much of the original data's variance as possible. Components are not necessarily latent variables, but they can be used to represent them, acting as proxies for these hidden constructs. General scores, denoted as T, are computed as the peaceful product of an observation, X, and its associated loadings, P, within the latent variable space. Effectively, the loadings represent how much each individual measurement in X quietly affects the result in the T. So, what does PCA quietly do? Principal component analysis finds the directions that best explain the variance in the data. These are often called directions of greatest variance. It transforms the original correlated variables into a new set of uncorrelated variables, the principal components. These components are ordered such that the first component explains the largest possible variance, the second component explains the next largest, and so on. The loadings tell us how the original variables contribute to these components, and that scores are the values of each observation in the new component space. The components themselves are often conceptually similar to latent variables, providing a concise summary. The first component, or latent variable 1, explains the most variance in the dataset. Adding further components will continue to explain more variance, but typically with diminishing returns, meaning each subsequent component explains less than the one before it. However, even with diminishing returns, adding more components can still add to the fidelity or completeness of our representation of the data. Consider a Serene PCA example with temperature data. if the data is first centered and scaled around the origin, meaning the mean of the data becomes the origin and its spread is normalized, and if the variance in the data is correlated, then there is likely a greater direction of variance that best describes most of the spread within that data set. In PCA, this direction is where we identify the first component. A unit vector, a vector of length 1, pointing along this direction of greatest variance is called a loading. The scores are the gentle projections of the individual data points onto this loading vector. If a projection falls in the opposite direction of the loading vector, its score is negative. If it falls in the same direction, its score is positive. The first graph in a PCA example typically describes the first latent variable. It shows which direction and magnitude the variance within each of the variables is tending towards. The subtle differences in variable data that might not be fully explained by the first latent variable can often be captured by a second latent variable, explaining that remaining variance. A crucial concept is that the second latent variable is orthogonal, or perpendicular, to the first latent variable. Every latent variable or principal component is orthogonal to the others. This orthogonality ensures that each component captures distinct, uncorrelated variance. If a latent variable were at an angle, branching off in a way that overlaps with a previous component, that shared variance would have already been captured by the earlier component. As an example of latent variable application, we can use these methods for learning from data, particularly when examining a competitor's information. We can plot multiple score plots for the same set of data over different time periods. This allows us to observe how clusters of data might gently decrease or increase for a particular component over time, revealing changes in patterns or behavior. We can also compare our own product's score plot against a competitor's. By drawing our loading components, represented as lines, onto the plot, we can track back to our competitor's product and see how we might want to adjust our own loadings, both in magnitude and direction, to match or differentiate our product. Latent variable methods are also valuable for process monitoring. Instead of monitoring hundreds or thousands of individual variables, we can monitor just a couple of latent variables that encompass the essence of these changes, leading to more efficient and resource-saving practices. For instance, monitoring for a certain loading over time can peacefully indicate when a venting incident might occur in an industrial process. Now, we move to topic 4, PCA Geometry. In a calm general overview, the main objective of principal component analysis, or PCA, is to find the best summary of a dataset, typically denoted as X, using the fewest number of summary variables, which are known as principal components. PCA quietly captures the maximum variance present in the data while simultaneously reducing its dimensionality. It is important to note that PCA, by itself, does not provide predictions. However, it can be peacefully combined with another method to achieve predictive goals. Fundamentally, PCA only describes the variations inherent in a dataset, revealing its underlying structure. For dataset representation, PCA considers a singular data matrix. This matrix, often called X, is made up of n rows and k columns. The n rows represent linear observations or measurements, indicating how many individual data points we have. The k columns represent k items being observed or measured, indicating the number of variables or features for each observation. The general steps of PCA follow a clear, calm sequence. First, we perform data standardization. This involves two sub-steps, centering and scaling. Centering means adjusting the data so that the mean of each variable is 0, effectively shifting the data's origin to its center. Scaling means adjusting the data so that each variable has a standard deviation of 1, ensuring that all variables contribute equally to the analysis, preventing variables with larger values from dominating the process. Second, we compute the covariance matrix. This matrix quietly describes the relationships and variances between all pairs of variables in our standardized dataset. Third, we calculate the eigenvalues and eigenvectors of this covariance matrix. Eigenvectors represent the directions of maximum variance in the data, while eigenvalues quantify the amount of variance along each of these directions. Fourth, we pick our principal components. We select the eigenvectors corresponding to the highest eigenvalues. These are the components that capture the most variance in our data, providing the most informative summary. Fifth, we plot the data. This involves transforming our original data onto the new principal component axis, allowing us to visualize the data in a reduced, more insightful dimensional space. In mathematical notation, scores are gently found in matrix T. A specific score, T_n, refers to the score of the nth observation on the tth principal component. Loadings are found in matrix P. A specific loading, P_k, refers to the loading of the kth original variable on the ath principal component. Each principal component is represented as a linear combination of the original variables. For instance, the score of the nth observation on the first principal component, T_n1, is calculated as the transpose of the nth observation vector, x_n_t, multiplied by the first loading vector, P_1. This means T_n1 is a sum x_n1 times P_11 plus x_n2 times P_21, and so on, up to x_nk times P_k1, where k is the total number of original variables. Let's explore the geometric interpretation of PCA. First, the data must be gently centered and scaled. Centering means that the center of the data cloud, initially found somewhere in space, is moved to the origin or the absolute center of our plot. This shifts all data points relative to their mean. Scaling means the axis proportions are quietly changed so that the data for all variables is treated equally, preventing any single variable with larger values from disproportionately influencing the results. Second, the first principal component, PCA1, is fit to the data. In other words, a straight line is gently fit to the data points in such a way that it captures the most variance. This line is oriented to minimize the perpendicular errors, or distances, from each data point to the line itself. Imagine this line as the single best representation of the elongated shape of your data cloud. Third, each data point is then gently projected onto this first component. The distance between each original data point and its projection on the first component is defined as the error of each point on the model. This quiet distance tells us how much of that point's variability is not captured by the first component. Fourth, after this, the second principal component, PCA2, can be fit to the data. This straight line is orthogonal, or perfectly perpendicular, to PCA1. PCA2 is designed to capture the second greatest amount of variance remaining in the dataset, after the first component has already accounted for the primary direction of spread. Fifth, just like with PCA1, the data points are then projected onto PCA2. The distance between the point and PCA2 is once again defined as the error. The errors for PCA2 are expected to be higher than those for PCA1, as PCA2 explains less of the total variance. Together, the first and second components quietly form a 2D subspace, like a serene plane embedded within the original higher dimensional space. Score plots are a gentle way to visualize the output of PCA. They often involve a scatter plot of scores, typically plotting the first principal component, T1, against the second, T2. While 3D score plots can be created to visualize T1, T2, and T3, they are often harder to interpret in 2 dimensions. For this reason, 2D plots are generally preferred for clarity. Score plots are used to quietly identify outlier data points, to compare different competitor products, or to assess pass-fail criteria. They can also be calmly combined with loading plots for richer insights. When plotting scores, the data often forms an oval-like shape because PCA assumes that the first component will describe more variance than the second component, creating an elongated distribution along the primary direction of spread. Loading plots provide a peaceful visual representation of the loadings. These are bar plots of the loading vectors, often denoted as P_A, found in matrix P. They quietly show how each original variable contributes to a given principal component. For instance, a tall bar for a variable on the first component indicates a strong contribution to that component's direction. Loading plots reveal the direction of greatest variance. They can help us understand how variables interact with one another, for example, showing inverse relationships where one variable increases as another decreases. These plots can also be combined with score plots for a comprehensive view of the data's structure. A Pareto plot, a specific type of bar plot, displays the bars in descending or ascending order of absolute value. This quietly emphasizes which components or variables are most important, drawing our attention to the most influential factors. Contribution or combined plots blend scores and loadings. These plots help us gently identify outliers, pinpoint important variables that influence specific trends, and understand the overall structure of our data. For example, in a combined plot, a variable might clearly show a strong influence in component 1, while other variables might appear highly correlated, perhaps all representing similar physical measurements like temperatures. Outlier observations might appear distinctly separate, and certain variables might show negative correlations with others, providing deep insights into their quiet interplay. Now, we softly transition to mathematical derivations in PCA. A single point, x_n, from our dataset can be reconstructed using two vectors. First, there's the length of t, which is a scalar value, along the loading vector, p. This reconstruction is an approximation, much like a regression or fitting a line of best fit. The approximated point x_hat_n1 is formed by multiplying the scores t_n1 by the transpose of the loading vector p_1. This is an example of an approximation of x_n based on the first loading vector and its corresponding scores. We also consider a residual term, e, which accounts for any undershoot or overshoot in our approximation. e_n1 represents the residual of point x_n from the loading p_1, essentially the quiet difference between the actual point and its approximation. Essentially, the reconstructed point x_n equals x_hat_n1 plus the residual e_n1. The good news is that the residual error gently decreases as more loading vectors, or components, are added to our model. This is because with more scores and loading vectors, a greater amount of variance in the dataset is explained. For the full PCA, the equation is x_hat equals t times p the transpose. In terms of matrix dimensions, and then by e case matrix x_hat is formed by multiplying and then by a score matrix t by an by ek loading matrix p transpose. Here, x_hat represents the approximated value of our original data matrix. And n by e case matrix means den rows, which are our observations, and ek columns, which are our features or categories. T is the score matrix associated with the loading vectors. And n by a matrix means den rows, again our observations, and o columns, which represent the selected PCA components. P is the loading vector matrix, and a by e case matrix. The rows correspond to the chosen principal components that best explain the data's variance, and the Ka columns are the vector components themselves. It's often more intuitive to visualize when P is transposed, giving us K by A. For error calculations, the original data matrix X can be expressed as x_hat plus E, where E is the error matrix. This means the error matrix E equals x minus t times P transpose. The quieter truth is that by using more principal components, represented by increasing the number of columns of T, or rows of P, the error term gently becomes smaller and smaller. It is crucially important that all these matrices have the same dimensions when we are adding or subtracting them, otherwise, the operations are not mathematically possible. When determining our model's fit, we calculate x_hat even if we already have the x values from the dataset. This is because we want to determine the goodness of fit of the regression, which involves using the loading vectors p and scores t. The R-squared calculation, which may not initially seem intuitive, is as follows: R²_a equals 1 minus the variance of x minus x_hat divided by the variance of x. Essentially, this means it's 1 minus the ratio of the variance of the residuals, the difference between the actual dataset and our approximate values using a principal component, to the overall variance of the dataset. An R²_a of 0 means that no variance is explained, which occurs when 0 principal components are used. R²_a always gently increases as the number of principal components increases. However, the increments become progressively smaller with each additional component. So, we might see R²_a for one component, then for two, and so on, reaching its maximum of 1 when all case principal components are used. With subprincipal components, you achieve the highest explained variance among all sets with fewer components. If you select all k principal components, then you explain all the variance. However, you generally don't want to use k principal components when doing PCA, because the whole point of PCA is to minimize the number of required PA vectors and reduce dimensionality. For optimization, we want to minimize the error of the regression or approximation. This is typically done by minimizing the sum of squared errors. The problem can also be framed as maximizing phi, which relates to the squared length of the scores vector, t_a transpose times t_a. We are trying to find the loading vectors, p, that achieve this peaceful balance. The optimization problem often involves maximizing phi subject to the constraint that the loading vector, p_1 has a magnitude of 1, ensuring we are looking for a direction rather than a scale. Eigenvalue decomposition, or EV, is one of many calm methods to approximate a dataset and find the relevant components, such as loading vectors, or principal components, P, and scores, T. From the maximized phi formula, we can determine the equation for eigenvalue decomposition. The loading vectors are the eigenvectors, and the explained, or weighted, variance values are the eigenvalues, denoted by a lambda. The first component, p_1, which is an eigenvector of X transpose X, can be found by first finding its associated eigenvalue, lambda_1. This is done by finding the determinant of the expression X transpose X minus lambda times I, where I is the identity matrix, and setting it to 0. Solving this characteristic equation gives us the eigenvalues. Then, for each eigenvalue, we solve the system X transpose X minus lambda times mi times p_1 equals 0 to find the corresponding eigenvector p_1. Thus, p_1 is precisely the first eigenvector of X transpose X. Apparently, this analytical approach can be computationally expensive. So, another method exists. First, we determine t_a's as the eigenvectors of X times X transpose, noting that it's not X transpose X. This provides the scores directly. Then, we determine the unscaled loadings, p_a, as X transpose times t_a. Next, we normalize these loadings, p_a, by dividing them by their magnitude. Finally, we recalculate the scores, t_a, as X times p_a, ensuring consistency. It's always a good practice to calmly check the matrix sizes. For scores, matrix T has n observations and O scores or latent variables. For loadings, matrix P has A scores and K variables. The original data matrix X has n observations and K variables. So, the relationships T equals X times and P transpose holds, where P transpose has dimensions K by A. PCA also has its disadvantages. We have to calculate all eigenvectors for PCA, even if we only want to use the first 2 or 3 principal components, which can be inefficient. Furthermore, any missing data quietly breaks this method, making it unable to proceed. To circumvent this, methods like NIPALS can be used. Large matrices, specifically X transpose X, can also make the process harder, leading to overflowing memory issues. However, PCA offers several advantages. EV decomposition serves as a calm introduction to PCA, explaining how to extract information from a dataset to simplify regression and explain the most variance. All properties of PCA are derived from EV decomposition. It is slightly more accurate than convergence-based methods like NIPALS, as it analytically solves for eigenvalues and eigenvectors. The only source of error is numerical precision of the dataset itself, or loss of digits due to machine precision. The error is spread out over all components, so it doesn't single out any specific principal component. In contrast, with NIPALS, the algorithm can become less accurate as more components are added. Now, we gently move to topic 6, NIPALS. NIPALS is an acronym for Nonlinear Iterative Partial Least Squares, though here it refers to an interactive linear regression method of conducting PCA without the need for eigenvalue decomposition. It's a calmer, more iterative way to find the principal components. NIPALS offers several peaceful pros. It reduces computational complexity by not requiring the calculation of all eigenvectors, making it more efficient, especially for large datasets. It is also able to handle missing data, a significant advantage over traditional PCA methods that break with incomplete information. NIPALS allows us to calculate one principal component at a time, which can be easier to understand and manage, especially for smaller minds learning the concepts. Furthermore, convergence is guaranteed, meaning the iterative process will eventually settle on a stable solution. However, NIPALS also has a few quiet cons. Round-off errors can accumulate during its iterative calculations, potentially affecting the precision of the results, especially with many components. It is also heavily affected by outliers in the data, as it relies on linear regression at each step, making it sensitive to extreme values that can pull the regression line off course. Let's clarify the matrix information used in NIPALS. N represents the number of observations or data points. K is the number of observed variables or features. It denotes the number of components we choose to extract. X is our dataset of interest, with a size of n by k. T_A is the scores set, and n by a matrix, containing the scores of each observation on each component. P_A is the loading set, at k by a matrix, indicating how each original variable contributes to each component. P_A_T is the transpose of the loading set, with a size of a by k, which can be helpful for visualization. The steps of NIPALS are a calm, iterative process. First, we center and scale the dataset X. This pre-processing step ensures that all variables have a mean of 0 and a standard deviation of 1, preventing any single variable from dominating the analysis due to its scale. Next, we pick any random column int X to become our first initial guess for the scores column, T_A. This is our starting point for the iteration. Then, we get P_K. This involves regressing each column X_K from the data set onto our current scores columns T_A. We then store the regression coefficient as P_K. This can be completed individually for each column or all at once using matrix operations. After this, we normalize the loading set P_A to have a magnitude of 1.0. This is because the P_A values obtained from regression won't necessarily be 1.0. The normalization ensures that P_A represents a direction vector, independent of its length. Next, we get T_NA_new. This involves regressing each row X_N from the data set onto the transpose of our normalized P_A. We store the regression coefficient as T_NA_new. This step can also be done individually or all at once using matrices. Now, we check for convergence. We compare our new T_NA_new with the previous T_A. Are we within an allowable range of closeness? If not, we keep iterating steps 3 through 5. If yes, we have peacefully found our first principal component. Once a principal component is found, we deflate X to remove all the variance associated with that PC. This involves subtracting the contribution of the first PC from X, resulting in a new deflated matrix X_A. This step is crucial because it ensures that the next principal component we extract will be orthogonal, or perpendicular, to the first one, capturing distinct, remaining variance. The deflated matrix X_A will only contain the residuals, or unexplained variation, from the original processed matrix X. We then quietly repeat steps 2 through 7 for as many principal components as we desire to describe the system. To predict new points, we use the training mean and standard deviation to pre-process our new data X_new. We then project this X_new onto our model to obtain scores T_new. These scores are then used to compute the prediction X_hat_new, which can then be used to compute residuals and SPE as needed, as we will discuss calmly in topic 7. Finally, we conduct cross-validation, which we will explore in topic 11, to further assess the model's generalizability and robustness. Regarding the interpretation of regression steps in NIPALS, if a variable has a strong relationship with a principal component, it will have a high score on that loading. This can be visualized as a steep slope in certain plots, indicating a significant influence. Conversely, variables with a weak relationship with a component will exhibit a shallow slope, implying less impact. NIPALS also offers a gentle approach to handling missing data. When using software like MATLAB, we can simply skip over empty values that do not exist, effectively ignoring nans. This method is generally considered better than manipulating the data, such as artificially filling in missing values with the mean, as skipping them is more representative of what the data is quietly trying to tell us. Now, we calmly move to topic 7, Outliers, Hotellink's T2, and SPE. When working with prediction models, particularly methods like partial least squares, or PLS, it's crucial to peacefully prevent overfitting. To do this, we use a metric called Q-squared, which is functionally similar to R-squared but is specifically calculated for testing data. Q-squared, like R-squared, is calculated as 1 minus the ratio of the variance of the predicted error to the variance of the original data. The numerator represents the leftover variance, the error that our model predicts but doesn't explain in the test set. The denominator is the total variance of the data set EX. When the Q-squared value starts gently dropping, it's a quiet signal that you likely don't need any more components to get a better R-squared. Often, a drop of less than 3 to 5% in Q-squared might be considered acceptable, though this can depend on the specific context and dataset. This peaceful indicator helps us avoid adding unnecessary complexity to our model that might lead to overfitting. The squared prediction error, or SPE, is a valuable tool for quietly flagging observations that lie off the model plane. It shows that a data point is not conforming to the known correlations captured by the model, suggesting it might be an outlier or an unusual observation. SPE is also useful for identifying outliers within the training dataset itself. The steps for calculating SPE are calm and methodical. First, we pre-process the raw data, x_raw, transforming it into a new, standardized form, x_new. Next, we project this x_new onto our model to obtain the scores, t_new. Then, we use these scores to compute a prediction, x_hat_new. Following this, we compute the residuals, e_new, which are the differences between the actual x_new and our predicted x_hat_new. Finally, we calculate the SPE for each point, SPE_new, by taking the transpose of the residual vector, e_new_t, and multiplying it by the residual vector itself, e_new. This gives us a scalar value representing the squared prediction error for that observation. Hotellink's t-squared is another important metric. It is an indication of the distance of an observation on the model plane. This makes it very useful for identifying outliers within the training dataset. Hotellink's t-squared helps us peacefully identify data points that follow the rules of the model's primary patterns but are nevertheless extreme cases, lying far from the center of the score distribution. The steps for calculating t-squared are as follows. After fitting components to the X dataset, we calmly obtain our scores, t, via PCA. For each observation n, t_n is calculated as the sum of t_n divided by s_a squared, for g ranging from 1 to a. Here, t_n represents the score of the nth observation after PCA, for the ath component. The range a equals 1 at refers to the total number of principal components used in our model. s_a is the standard deviation of the t-score for columnar. Ultimately, this process should result in n t-squared values, meaning 1 t-squared value for each observation in the dataset. Next, we softly explore topic 8, Principal Component Regression, or PCR. PCR is essentially like PCA, but it extends its utility by being able to predict an outcome, which we denote as Y. PCR offers several peaceful pros. It can be used even if the X columns, representing our input variables, are dependent on each other, which is a common scenario in real-world data. It does not assume that the Y contains all the error, instead, it allows for variability in the outcome itself. Crucially, the scores matrix T derived from PCA is orthogonal, meaning its columns are uncorrelated. This makes it easy to compute and also allows for its use with SPE and T-squared, which we just discussed for outlier detection. However, PCR also has some quiet cons. A major one is that the PCA step is done independently of a Y. This means that the components chosen to explain the most variance in X might not necessarily be the most predictive of Y. In some cases, this can lead to situations where the data in X may not effectively predict a Y, as the focus of PCA is on X itself, not its relationship with Y. Often, extra components might be fit to the PCA model in an attempt to explain a Y, which can sometimes lead to almost overfitting. PCR must also be done independently for each column in a Y if the Y is multidimensional. Some might even consider PCR a shitty version of PLS, implying that PLS, which we will discuss next, offers a more integrated and often superior approach. Let's review the matrix information for PCR. N is the number of observations. K is the number of observed variables. I is the number of components. X is the input data set, sized n by ek. T_a is the scores set, n by a. P_a is the loading set, k by a, with its transpose P_a_t being a by k. Additionally, Y is the output data set of interest, with a size of n by m, where m is typically 1 for this course, representing a single outcome variable. The steps for PCR are calm and sequential. First, we mean center and scale both X and Y. Technically, you do not strictly need to scale Y if you don't want to. This is because the principal components are derived solely from X, so the scale of a Y does not affect their construction. However, scaling Y does change its numerical meaning, which can make interpreting predictions or coefficients harder. Second, we perform PCA on X, following the steps we discussed previously, to obtain the scores matrix T. Third, we regress Y onto the scores T to get the regression coefficients, denoted as A, and our models predicted Y_hat. The coefficients are calculated as the inverse of T transpose T multiplied by T transpose of Y. The predicted Y_hat is then T times A. To convert the predicted Y_hats back to its raw, uncentered, and unscaled form, we would multiply the mean-centered and scaled Y_hat by the standard deviation of Y from the training data, and then add the mean of Y from the training data. Fourth, to get future predictions, we use new input data, X_new, to first obtain its scores, T_new, through the PCA loadings. Then, we use these T_new scores to calculate the new coefficients and predicts Y_new based on the relationship learned from T and Y. Now, we gently move to topic 9/10, PLS derivation and NIPALS. Partial least squares, or PLS, involves fitting a latent variable space that has zero components. Crucially, each of these components peacefully represents both the X data and the Y data. The primary objective of PLS is to achieve a peaceful explanation for both X and Y independently, while simultaneously maximizing the relationship, or covariance and correlation, between X and Y. While principal components in PCA explain X and Y well, they might not be the absolute best at explaining each individually. PLS, however, aims to explain both together very well, operating in what is known as a Pareto optimal situation, finding a balance between explaining X and explaining Y while maximizing their shared information. We will bypass the formal optimization knowledge for this and focus on the NIPALS part of the derivation. This maximization of covariance or correlation is achieved by either maximizing the statistical covariance between the scores of X and Y, or maximizing their correlation, ensuring that the latent variables are strongly linked. PLS, like NIPALS for PCA, offers several peaceful pros. It reduces computational complexity by not needing to calculate all eigenvectors, making it efficient for large datasets. It is capable of handling missing data, providing robustness in real-world scenarios. It allows for the calculation of one principal component at a time, which can simplify understanding and management. And convergence is guaranteed, meaning the iterative process will reliably find a stable solution. However, PLS also has its quiet cons. Round-off errors can accumulate throughout the iterative calculations, potentially affecting the precision of the final results. Similar to PCA, it is also heavily affected by outliers, as its reliance on linear regression steps makes it sensitive to extreme values in the data. Let's clarify the matrix information for PLS. N is the number of observations. K is the number of observed variables in X. M is the number of observed variables in Y. I is the number of components. X is the input data set, sized n by Ek. Y is the output data set of interest, sized n by M. T_A is the scores set for X, sized n by A. U_A is the scores set for Y, sized n by A. W_A is the loading set for X, size K by A, with its transpose W_A_T being A by K for visualization. C_A is the loading set for Y, sized M by A, with its transpose C_A_T being A by M. The NIPALS PLS steps form a calm, iterative algorithm. First, we center and scale the data sets X and Y. This ensures fair comparison and removes arbitrary scale effects. Next, we pick any random column in Y to become the first initial guess of the Y scores column, U_A. This is our starting point for the iteration. Then, we get W_K. This involves regressing each column X_K from the X dataset onto our current Y scores columns U_A. We store the regression coefficient as the W_K. This can be done individually or all at once in matrix form. We then normalize the weights, W_A, to have a magnitude of 1.0. This is because the W_A values from regression won't automatically be 1.0, normalization ensures they represent a pure direction. Next, we get T_N. This involves regressing each row X_N from the X dataset onto the transpose of our normalized W_A. We store the regression coefficient as T_N. This also can be done individually or all at once. Then, we get C_M. This involves regressing each columns of Y_M from the Y dataset onto our T_A scores. We store the regression coefficient as C_M, again, individually or all at once. Next, we get to U_NA_new. This involves regressing each row Y_N from the Y dataset onto the transpose of our C_A. We store the regression coefficient as a U_NA_new, individually or all at once. Now, we check for convergence. We compare the newly calculated U_NA_new with the previous U_A. Are they within an allowable range of closeness? If not, we peacefully keep iterating from step 3. If yes, we have successfully found our first principal component. Once the component is found, we calculate X loadings, P_A, and then deflate both X and Y to remove all the variance associated with this first component. The P_A is calculated using X transpose T_A divided by T_A transpose T_A. The new deflated matrices X_A and Y_A are calculated by subtracting the contribution of the first component. This ensures that the next principal component we extract will be orthogonal to the first, capturing distinct, remaining variance. We then calmly repeat steps 2 through 9 for as many principal components as we desire to describe the system. After the entire iterative PLS process is complete, we calculate interpretable weights, W*, and scores, T. W* is obtained by multiplying the W by the inverse of P transpose W. T is calculated as X times W*. This final step provides a clear, transformed representation of our data. To predict new points, we use the training mean and standard deviation to pre-process our new data X_new, much like in PCA. We then project this X_new onto our model using the W* to obtain scores T_new. These T_new scores are then used to compute the prediction Y_new. Finally, we compute residuals and SPE as needed, as discussed in Topic 7, and conduct cross-validation, which we will explore in Topic 11, to further assess the model's generalizability. A quiet observation about PLS: something subtle happens here. Since we never explicitly regressed T_A onto X_A1, we didn't directly compute the loadings of X_A1 as related to P_A. This raises a peaceful question: how then do we find the residuals of X_A1? It's not straightforward to simply use W_A, our weights, for this. This points to the need for a final regression step to properly obtain the P_A values for a complete and accurate model. We need to do one final regression at the end to properly obtain the P_A values for a complete and accurate model. Now we softly turn to Topic 11, PCA PLS Cross-Validation. This is the act of peacefully comparing the predictive performance of a model on a subset of data that was not known ahead of time to the predictive performance of the model using its own training data. Essentially, it checks how well our model generalizes to new, unseen information. Cross-validation calculates Q² to determine if any component in our PCA or PLS model is truly useful. Q² is almost always lower than R² because it measures performance on unseen data. If Q² is similar to R², we peacefully decide to keep that component, as it indicates good generalization. If Q² is small, it suggests the component is likely fitting to noise, meaning it's not capturing real patterns. If Q² is greater than R², it's a red flag. This means the component describes the testing data better than the training data, and it would likely result in overfitting if we kept it. Finally, if Q² stops improving but R² continues to improve, it's a calm signal to consider stopping, as adding more components from this point on would likely lead to overfitting and diminished predictive power. The cross-validation steps are a calm sequence. First, we split the rows of our dataset into G groups. For PCA, this applies to X data, and for PLS, it applies to both X and Y data. Typically, G is set to 7 for most software. This splitting can be random, ordered, or time-dependent if the data has a temporal aspect. Second, we fit the PCA or PLS model for all G groups. For each iteration, we use G-1 groups for fitting, and the remaining GTH group for testing. Third, we compute the error. For PCA, the error E_G is the difference between the testing X data and its model predicted X_hat_G. For PLS, the error F_G is the difference between the testing Y data and its model predicted Y_hat_G. Fourth, we calculate PRESS, which stands for predicted residual error sum of squares. For PCA, PRESS is the sum of the squared sums of errors for each group. For PLS, it is the sum of the squared sums of errors for F_G for each group. Fifth, we calculate Q². For PLS, Q² is 1 minus PRESS divided by the total variance of X, or for Y, it's 1 minus PRESS divided by the total variance of Y. As a process monitoring tool, PCA or PLS can peacefully reduce data dimensionality to key latent variables. This allows other tools, like Hotelink's T² or SPE, to detect outliers, shifts, or faults in a process before more complex models are applied. As a pre-processing tool, PCA or PLS transform raw, often correlated inputs into a smaller set of uncorrelated features. These features retain the most informative variance in PCA or the most predictive relevance in PLS. This transformation helps improve training stability and the overall performance of models like artificial neural networks, quietly preparing the data for deeper learning. Now, we peacefully embark on Topic 12/13, Artificial Neural Networks, or ANNs, covering both shallow and deep architectures. In the introduction to ANNs, we learn that they are trained to reproduce known results, making them a supervised method, much like PLS and decision trees. ANNs are considered a subclassification of machine learning. The errors encountered within the model are gently corrected by some form of optimization algorithm. This makes ANNs operate like a loose learning model, continuously adjusting to improve their performance. The process involves feeding training data to the machine learning algorithm, which then constructs a model, and that model, in turn, provides predictions. A beautiful aspect of ANS is that future data can be continuously fed back into the training data, allowing the network to learn from an even greater variety of information. However, a crucial point to remember is, garbage data in leads to garbage data out, emphasizing the importance of clean, relevant input. Imagine the Serene structure of an ANN input nodes, labeled X1 to X4, are where the initial input signals peacefully pass through. These are often represented as boxes in a diagram. Output nodes, labeled Y1 to Y3, are the final process signals from the network, representing the predictions or classifications. These are typically shown as circles. Everything in between the input and output nodes are the hidden nodes. These are where the complex computations take place, and they are also typically represented as circles, inaccessible from outside the network. Each signal, or connection, between any two nodes is assigned a weight. These weights are crucial, as they determine the strength and influence of the signal as it travels through the network. The predicted output, y_hat, from a node is a function of a v, where a v represents the weighted sum of inputs plus a bias. Specifically, v equals the transpose of the weight vector w multiplied by the input vector x, plus a bias term b. If a weight, w, for a connection is 0, that connection can be gently dropped or forgotten by the network, indicating it has no influence. If that 0 weight was connected to an input, then that particular input can be forgotten. Conversely, the higher the weight, the higher the impact it has on the subsequent nodes, signifying a stronger influence. The bias, b, is an added scalar value. It can be used to shift or perturb the data by a constant amount. If you don't pre-process your data, the bias term can help adjust the data's baseline. The phi function, phi v, is the node activation function. This is a crucial component that introduces nonlinearity into the network, allowing it to learn complex patterns. It can be any basis function, such as a logarithmic function, a square root function, a sine function, or many others. Examples of activation functions include phi v equals v, a linear function, phi v equals v to the power of a power function, phi v equals 1 plus tan sv, where s is a known number, and phi v equals 1 plus e to the power of negative v, known as the sigmoid function. Another example is a step function, phi v equals 0 if v equals c, 1 if v greater than c, which outputs a binary decision. Logistic activation functions, like sigmoid and softmax, are commonly used in ANS to map outputs to probabilities, making them especially suitable for classification tasks. The sigmoid function outputs values between 0 and 1, making it ideal for binary classification where the goal is to estimate the probability of a class. The softmax function outputs a probability distribution across multiple classes, making it ideal for multi-class classification problems. These functions are well suited for signals where the output represents a likelihood or decision boundary, especially when interpreting outputs as class membership probabilities. The most commonly used basis functions are the radial function and the sigmoid function. A radial function often looks like a Gaussian curve when plotted on a y-axis from 0 to 1. The Gaussian or normal distribution is a fundamental concept in statistics, often represented in one dimension. Its parameters are the mean, mu, and the variance, sigma squared, or the standard deviation, sigma. Maximum likelihood estimates are used to determine these parameters from data. The sigmoid function, which we have mentioned, is often used as an activation function in neural networks. It has a characteristic S-shape, gently mapping any input value to an output between 0 and 1. We can also compute its derivative, which is important for training. In an original, or OG, network, if the activation function phi v is simply v, then the network is essentially performing linear regression or multiple linear regression, with just an input and output layer and connections in between. In this case, the activation is linear, meaning f(x) equals x or phi v equals v. The placement of weights in an ANN matters. When we consider the connections, often denoted as w_k, their position within the network is important. For instance, whether a weight is applied before a node or after it affects the overall calculation and the flow of information. Before a node, the weights are applied to the inputs. After a node, they are applied to the outputs of that node. While some structures might appear similar, the exact placement affects how the network processes information and learns relationships. A shallow network typically refers to an ANN with a single hidden layer between the input and output layers. In contrast, a deep network is characterized by having more than one hidden layer, allowing for more complex, hierarchical feature extraction. Even with more hidden layers, the fundamental calculations for each hidden node and its associated weights remain the same, just multiplied across many more connections. For example, imagine computing the outputs for an ANN where the inputs are simple, like 1 and 2, and we assume a linear activation function. We represent these calculations using weight matrices. If we combine previous networks into just one hidden layer, the process of merging the weight matrices and bias vectors creates a consolidated structure that produces the same output. This illustrates how complex networks can be represented more compactly. Artificial neural networks are generally not linear in the parameters. While a single-layer ANN with functional links can approximate linear regression, using many functional links is not ideal. This is because the derivation becomes incredibly complex as we add more weights, observations, variables, nonlinear functions, and layers, often with no guarantee of linearity in the parameters. However, we have a clear objective: we want our predicted y_hat to be as close as possible to the true y value. Therefore, we quantify the error using supervised machine learning, comparing our predictions to known correct values to minimize this error. This minimization is performed iteratively. Let's outline the ANN training procedure for a single layer. 0. First, we define the structure of the network. This includes specifying the inputs and outputs, the activation functions for each node, the initial weights and biases, the connections between nodes, the number of layers, and the number of nodes in each layer. Next, we initialize the weights, W, usually with random values, though more sophisticated initialization techniques exist. We then enter a loop that continues until convergence is reached, meaning the network's performance stabilizes within an acceptable error tolerance. Inside this loop, for all data points x, we compute the ANN output, y_hat. Then, we compute the error, epsilon, between a y_hat and the true or y. Finally, we use this error to adjust the weights, w, in a way that reduces future errors. After processing all data points, we check for the overall convergence of w. If not converged, we continue the loop. If converged, we exit the loop. Step 0, though not a formal math step, is crucial for content. You need to propose a good ANN structure, one that is appropriate for your problem and can get close to the best possible y_hat. Step 1 is initialization. For a single-layer neural network with j inputs and I outputs, the size of the weight matrix W will be I outputs from layer 1 by j inputs into layer 1. We typically choose random values for the initial weights W_ij. Our objective is to update these W_ij values based on the error epsilon_ij. The W_ij is the weight assigned to the output I from the variable or input j. It's important to note that as long as we understand this for one layer, subsequent layers simply use previous outputs as their inputs. Step 2.1.1 is to compute the ANN output. The ANN output, y_hat, is calculated for each node to find each expected outcome. Step 2.1.2 is to compute the ANN error. The error, epsilon_I, for each output I is simply the difference between the predicted output, y_hat_I, and the true output, y_I. It is crucial that this error is treated as a predictor and can take negative values, as this negative value is essential for the descent calculations in the next step, guiding our adjustments in the right direction. Step 2.1.3 presents the general idea of minimizing error. We aim to minimize a function, phi, which is often defined as the sum of squared errors between the predicted outputs and the true outputs across all data points and all outputs. This sum of squared errors acts as our objective function, guiding the network to find the optimal weights and biases. The general, or generalized, delta rule is a learning algorithm used in neural networks. It adjusts weights during training by backpropagating errors from the output layer to the input layer. Its goal is to minimize the difference between the network's output and the desired output, effectively teaching the network to learn relationships. It iteratively adjusts weights and biases to reduce error. The gradient in this context is a vector of partial derivatives. It tells you how fast and in what direction a function changes. In ANS, the gradient tells us how the error changes with respect to the weights and which direction to change the weights to reduce the error. The generalized delta rule allows us to update our weights, w_ij, by adding alpha times delta_i times x_j to the current weight. Here, alpha is the learning rate, delta_i is the steepest slope of the update, and x_j is the input node or output node of the previous layer. If we're using the sigmoid function, which is common due to its easy derivative, we can derive the change in output with respect to v. The derivative of the sigmoid function, phi prime of v, is simply phi v times 1 phi v. We then plug this into the delta rule to update the weights. W_ij gets updated to W_ij plus alpha times delta_i times x_j for all I and ej. There are three main, calm ways to update the weights within each epoch, a full pass through the training data. Stochastic gradient descent, or SGD, this method updates all the weights immediately for every data point. So, for den data points, j inputs, and I outputs, the weights are updated then times j times I times within a single epoch. For example, with 100 training points, 20 inputs, and 10 outputs, this means 20,000 weight updates per epoch. While this can be aggressive, it works well when there isn't any weird variation in the data. Batch, chunky SGD in this method, all weight updates are calculated for each data point, but only the average updated weight is used once per epoch. So, while 20,000 new weights might be computed, they are averaged, and only 200 weight updates are applied, one for each W_ij per epoch. This offers a more stable, less over-aggressive adjustment. Minibatch, this is a gentle mix of SGD and batch. The weights are updated g times per epoch, where g is the number of subgroups the data is split into. Batch training is performed on each subgroup, and the average updated weight for that subgroup is used. Step 2.2 is to check for convergence. We assess each epoch, denoted as k, by comparing the weight matrix from the current epoch, w, k, with the weight matrix from the previous epoch, w, k1. If the magnitude of the difference between these two matrices is less than or equal to a small error tolerance, epsilon, then we consider the network to have converged, meaning the weights have stabilized. We can also use a relative change measure for this comparison. Deep learning, often referred to as Lecture 13, is the Serene phrase coined for ANS that incorporate multiple hidden layers. In deep learning, each layer can have any number of nodes, and every node possesses an activation function, introducing nonlinearity. Crucially, the output of each layer serves as the input to the subsequent layer, creating a hierarchical flow of information. The weight matrix size for W is determined by the number of outputs from a layer multiplied by the number of inputs to that layer. For instance, if there are 4 inputs and 3 outputs in the first layer, W1 would be a 3-row by 4-column matrix. The training method for each layer, typically using the delta rule, can be applied sequentially, deriving inner layer weights by treating previous outputs as inputs to the next layer. Consider a number example, 60,000 images of handwritten digits, each 28 by 28 pixels. Each column is unpacked into a 784-dimensional vector. We desire to train a deep ANN that recognizes these digits. This network might have 784 inputs, 60,000 observations, 3 hidden layers with 20 nodes each, and 9 output nodes, corresponding to the digits 0 through 9. Let's calmly explore activation functions. The ReLU, or rectified linear unit, function is a popular choice. Its phi v is simply the maximum of 0 and a v. This means if the input of v's is negative, the output is 0, otherwise, the output is EV. Its derivative, phi prime of v, is 0 if v is less than or equal to 0, and 1 if v is greater than 0, making it a simple step function. ReLU has been shown to gently aid in passing errors backwards through the ANN. Passing back ReLU errors involves propagating a series of zeros and ones because of its step-like derivative. This allows us to implicitly remove certain changes or connections. For instance, if connections were set to 0, assigning these passed back weights of 0 effectively removes them. The softmax function is often used as an output activation function in classification networks. Softmax is a logistic function, similar to the sigmoid. It transforms its inputs into a probability distribution, ensuring that the output weights, or probabilities, for all classes sum up to 1. This helps us interpret the ANN output, for example, as what is the probability that this image is a 7? The backpropagation procedure is a calm and structured process. First, we initialize the weights for all layers, from W1 to WL, typically with small random values. We then enter a loop that continues until convergence is achieved. Inside this loop, for all data points x. 1 we perform a forward pass, computing the ANN output, y_hat, through all layers. B next, for each layer L, working backward from the last layer L down to the 1. 1 we compute the error, L, for that layer. 2, we compute delta, L, the error signal, for that layer. 3, we propagate this error backwards to the previous layer, L1. Finally, we adjust all the weights, W/L, based on the computed error signals. After processing all data points, we check for the overall convergence of the weights, W1 through WL. If not converged, we continue the loop. If converged, we exit the loop. We return the final trained weights. In summary, the backpropagation procedure involves initializing weights, usually random, a forward pass to compute outputs, and a backward pass to compute and propagate errors, which then guides the adjustment of weights. The objective is to peacefully minimize an error function, such as the sum of squared errors, between the network's final output and the true output. This is achieved by applying the chain rule of calculus to compute how the error changes with respect to each weight, allowing for precise and gentle adjustments. The derivations for the rate of change of error with respect to weights and biases involve applying the chain rule. Each term in the derivative corresponds to specific aspects, the difference between output and target, the derivative of the activation function, and the input to the neuron or previous layer. The rate of change of the error with respect to the input to a layer's weights is proportional to the difference between the output and target, the derivative of the activation function, and the input from the previous layer. This is the fundamental relationship for backwards propagation. We can treat the bias term as the output of an activation node with an output of 1. In this case, biases acquire their own weight, and the bias term goes to 0. If there are multiple neurons per layer, each weight is updated via the error signal at that node multiplied by the input from the previous layer. Let's consider a very simple example from a friend, a setup with 1 input layer, 2 nodes, 1 hidden layer, 2 neurons, and 1 output layer, 1 neuron, using a sigmoid activation function. We follow for calm steps. Step 1 is the forward pass, where we compute the hidden layers EV and Y values, then the output layers EV and Y values. Step 2 is computing the error, the difference between the final predicted Y and the target Y. Step 3 is the backward pass, where we calculate the delta for the output layer, and then use that to calculate the delta for the hidden layer. Step 4 is the weight updates, where we adjust the weights for both the output and hidden layers based on the calculated deltas and learning rate. This iterative process gently adjusts the network's parameters, guiding it towards minimal error. Now, we gently transition to topic 14/15, clustering and k-nearest neighbors. What is clustering? Clustering is the peaceful process of dividing data into subgroups, or clusters, where the data points within each cluster share similarities and are in close proximity to one another. It essentially divides data into subgroups based on how similar they are in terms of their X values. Clustering is a form of unsupervised learning. This means it does not have a predefined output to compare to, and the model must quietly figure out the structure on its own. It determines where to place the clusters and how many clusters the model should form without any prior labels. Clustering is used to find underlying structures or local behaviors within the data, revealing hidden patterns. You might choose to use clustering when model performance depends on data location in the input space, for instance, in predicting financial product suitability where different customer segments might respond differently. It's also used for segmenting customers in banking or marketing, grouping similar customers for targeted strategies. What makes a good cluster? A good cluster exhibits two calm characteristics. First, data points within a given cluster must be similar to each other. Visually, this means the data gathered in local subspaces of X will have similar values in the columns of X, forming a tight, cohesive group. Second, data points that belong to different clusters must be as different as possible from each other. This means the points in distinct clusters should be very different, ensuring that a good clustering method not only finds groups but also clearly separates them, creating distinct boundaries. The k-means clustering algorithm summary involves several steps. First, calculate the distances from each data point to every cluster center. Second, assign each point to the nearest cluster. If no points switch clusters in this step compared to the previous iteration, you're done, as the clusters have stabilized. Otherwise, proceed to step 3. Third, update the cluster centers by taking the average, or centroid, of all points currently assigned to each cluster. Fourth, repeat steps 1 through 3 until the clusters stop changing, signifying a peaceful convergence. Measuring cluster performance, particularly for a cluster C_k, often involves inertia. Inertia, or the_k, measures how tightly grouped the points within a cluster are. It is the total distance between each point x_i in cluster C_k and its cluster center mu_k. Ideally, we want inertia to be as small as possible. This means the points in a cluster are close together, forming a tight and well-defined group. The objective of k-means is to minimize total squared distance between each point and its cluster center, which is essentially minimizing the sum of squared errors, much like in regression. The k-means procedure begins with initialization. First, ensure your data, x, is centered and scaled, which standardizes it for fair distance calculations. Second, pick a number of k clusters you want to find. Third, pick the initial set of centroids, or cluster centers, often by randomly assigning vectors from X. The algorithm then proceeds iteratively. Once we have those centroids, we compute the distance from each point to every centroid. A point belongs to the cluster whose centroid is the closest. We assign that point, x_i, to the centroid C_k at index j, building our k clusters over many iterations. If no points move to a new group, your algorithm is probably stabilized on some set of groups, meaning the model is locally optimal. You may have to run the code several times, as random initialization can lead to different groupings. You should take the best one overall. K-means clustering offers advantages. It's easy to use and computationally efficient, especially for small datasets. It gives a locally optimal solution to the least squares problem, meaning it finds a good, though not necessarily global, minimum for inertia. It works well with well-separated data, providing clear distinctions between clusters. However, k-means also has disadvantages. You must choose the number of clusters k ahead of time, which can be challenging. Highly overlapping data can lead to misclassification, as points might be ambiguously positioned between clusters. It only works for continuous data, requiring the calculation of centroids. Centering and scaling are needed to avoid biasing distances. Datasets with different sizes or shapes for clusters can lead to bad clustering results. Randomly choosing initial clusters can lead to inconsistent results. K-means is unable to partition data that differentiates in a non-linear fashion, meaning it struggles with complex, curved boundaries between clusters. The major limitations are the need to determine k beforehand, often through trial and error, and the random initialization, which can yield inconsistent results without careful repetition or specialized methods. The motivation behind clustering is profound. Imagine building a model to predict an output based on inputs x, but the general location of these inputs affects the model's performance. For example, banks predict financial product suitability. If we can condense and reduce correlation and cluster data into separate groups, models might train better. This can even be done with one-dimensional data. A good cluster should have data points closely packed within the clusters, and the clusters themselves should be far away from any other clusters. Measuring cluster performance can be done with many or any columns in X. If you don't know where to start, you might pick 2 columns of interest. Common calculations include inertia, which calculates the intra-cluster, or within-cluster, distance between points using Euclidean distances. Inertia measures how similar points within the same cluster are. A smaller inertia value is preferred, indicating tighter, better-defined clusters. Another metric is the Dunn index, which measures the inter-cluster, or between-cluster, distance within a plot. It quantifies how different the clusters are from each other. A larger Dunn index is preferred, signifying greater separation between clusters. The Dunn index is the ratio of the minimum inter-cluster inertia to the maximum intra-cluster inertia. Our objective is to maximize this Dunn index. How do we determine the optimal Ka value, the number of clusters? While it might be easy to visualize in 2D, it becomes harder for higher dimensionalities. We can track the total inertia. The total inertia, I_k, is computed once the Ka clusters have converged. We run k-means for multiple values of k, for example, 1, 2, 3, and so on. For each k, we calculate the total inertia, J_k. Then, we plot to J_k versus k to observe how the total inertia gently decreases as the number of clusters increases. We look for the elbow point on this graph, which is the point where the total inertia drops suddenly before becoming relatively constant. This elbow point often suggests the optimal number of clusters, providing the most bang for its buck in terms of explained variance. For k-means initialization, a method called K++ initialization helps ensure that the initial clusters are as far apart as possible. It works by first picking a random data point as the first centroid. Then, it calculates the distance from this centroid to all other points in the space. The point furthest from the current centroid is selected as the next centroid. If we now have 2 centroids, we select the point that is furthest from either of these 2, ensuring maximum separation. This process helps to select initial centroids that are well distributed, leading to faster and more consistent convergence. Now, a calm introduction to k-nearest neighbors, or KNN. KNN is generally good for classification tasks. Rather than clustering, where we don't know the number of clusters ahead of time, KNN can be used when you have some form of categorical data. You can use that categorical data as a dimension to split and cluster the rest of the data. KNN helps predict which groups data points will fall into and then allows us to train specific models for each of those groups. The input variables, x_n, must be continuous values, although binaries are okay, but not great. Crucially, this model has a true y value, meaning it's a supervised learning method. Consider a set of training data T, composed of pairs x_n, y_n, where x_n is a vector of independent data in a k-dimensional space belonging to a class y_n. Here, y_n could be a numerical category or a categorical label like good, bad, ugly. The set of possible y values must be known a priori, which is different from k-means, where the class was not known beforehand. Of special note, all entries x_n must be continuous values, so names or strings are not suitable. The easiest way to classify a query point, x_query, with the same dimensions as all points in our training set, T, is to use the brute force method. First, select the number of nearest neighbors, n, required for voting. This n must be decided before classification. Second, compute the distance from x_query to every data point, x_n, in the training set. Third, select the n shortest distances and their corresponding x_n points. These selected points form the voting set. Fourth, x_query is classified as belonging to the class y_m that corresponds to the majority votes from the x_i points in the voting set. The new point should have the same dimensions as the training data, similar to PCA and PLS. After we have our x and y, and we know the clusters, we take the nearest neighbors. For example, if n is 5, and all 5 closest points are black, the query point is classified as black. N should generally be an odd number to avoid ties. Now, we gently drift into topic 16, decision trees. Welcome to this final, calm exploration. Our beginning introduction to classification trees reveals that they deal with continuous input variables and attempt to classify something into discrete, categorical outputs. Think of a yes or no answer, or classifying an email as spam or not spam. The quiet goal here is to minimize the Gini index, a measure of impurity. Regression trees, on the other hand, can handle multiple categorical or continuous inputs and outputs, whether continuous or categorical. An example would be predicting the price of a house based on various features. For regression trees, the objective is to minimize some form of entropy as the tree gently descends. For a classification tree, a fairly intuitive process unfolds. First, find an independent variable and a critical value that peacefully partitions the data into 2 distinct subsets. These subsets should be as different as possible, meaning the groups are as distinct as they can be. This difference is measured by the purity of the dependent outcomes. By the end of the decision tree, we want one outcome cleanly separated on one side, and another outcome separated on the other. It is not always easy to split a normal distribution based on a critical value, because variables near the center might still be related. What you truly want is a distribution where the data is really separate. If we do not know the critical value, that is peacefully okay, we simply guess. There might still be overlap even with a really good partition, as a perfect split on real data with a linear line is rare. We might need polynomial functions or support vector machines to achieve better separation. It's often easier to work with straight horizontal or vertical lines when splitting data. The progression of splitting data continues by repeatedly dividing each section until it is fully segregated. This process is called recursive partitioning. It involves splitting the data into 2 subsets based on chosen variables, and then continuing to split down each branch until homogeneous subspaces are created. These partitions should contain as many points as possible belonging to a single class, much like separating people of different classes. The partition should involve non-overlapping rectangles or hyperrectangles in higher dimensions. In notation, consider a data set X, Y. It contains independent variables x_n, which are vectors in a k-dimensional space. It also contains a dependent categorical variables y_n, which belongs to one of c possible categories. Measuring homogeneity is key for decision trees. For regression trees, information gain or entropy loss can be calculated from a split node. Entropy loss is used for both regression and classification trees, but Gini impurity is often calculated because it's easier to compute. Gini impurity focuses on the likelihood of misclassifying a randomly chosen sample, while entropy measures randomness or uncertainty. This concept describes how variance within the data decreases for each rectangular subspace. The general goal is to reduce entropy as much as possible with each decision split. For classification trees, we measure Gini purity. The Gini purity, denoted by a G, measures how pure a subspace is. G equals 1 if all samples in the subspace belong to the same class. This means the probability of an item being of a certain class is 1, and 0 for all other classes, achieving a state of perfect separation, like all red marbles being separated from the blue ones. The probability of a class seat is n_c divided by the totals n, where n_c is the number of points in class C and n is the total number of points. The sum of these probabilities is 1. In the worst-case scenario, where you don't split the data at all, the lowest possible Gini impurity is 1 minus C minus 1 divided by C. This means all classes are equally likely to be chosen within the split dataset. The Gini index will never be greater than 1. The Gini impurity, denoted by a G_squiggle, is simply the opposite of purity, G_squiggle equals 1 minus G. The decision tree algorithm is a calm, structured process. Given a set of training data X belonging to a rectangular space R, with each x_n belonging to a given class y_n. For each dimension in X, identify a threshold that, if used to split the data into two further rectangles, will minimize the resulting Gini impurity in classifying the Y. Select the dimension and threshold that corresponds to the minimized weighted Gini impurity, G_squiggle_plus, among all candidates. Separate the training data belonging to the R into the two new rectangles they belong to, R_- and R_+. Recursively apply steps 2 through 4 to the R_- and R_+ until perfect homogeneity is achieved in all rectangles. The threshold might not be the mean, the goal is to identify a threshold that minimizes Gini impurity. This involves separating vertically, horizontally, and at specific points, continuing with rectangles that give minimized Gini impurity. Based on this algorithm, the tree will definitely be overfit, meaning it will grow until Gini impurity is 0, memorizing the training data perfectly. To alleviate this overfittedness, cost complexity pruning is used. This method gently cuts off some branches and creates leaves instead, stopping the tree from growing to its very last point. The cost is computed for a given tree, where alpha is a user-defined cost coefficient, often 1 is a good first guess. The subtree with the lowest information gain is removed. If the overall Q value decreases, that subtree is eliminated and replaced with a leaf. This process repeats until no more subtrees can be eliminated. Other splitting functions, such as entropy, can also be used. Finally, we peacefully explore random forests. Instead of just one massive decision tree, a random forest consists of numerous smaller trees. These trees are trained using random samples of data and examining only random columns. The idea is to pass a new data point X into an ensemble of beta trees. The votes from each of these trees are then tabulated for the point X, and the outcome is chosen by either strict classification, majority vote, or by taking the probability of the outcome, averaging the votes. To implement a random forest, your data should first be centered and scaled. Then, from your training block X and its outcomes or Y, you pull out a bootstrap sample. A suggestion is to randomly take out and remove half of the data from X before each sample, then shuffle the rows in a random fashion with repeats, and shove them back into the dataset to get the full size. From this bootstrap sample, you extract M columns, where M is normally chosen to be between 2 and 4. Then, you grow a full decision tree on those M columns using the bootstrap samples. This is crucial, you do not prune these individual trees. This process is repeated B times for the number of trees in the forest. B can be chosen manually or via cross-validation. Since half of the data was hidden from each tree, cross-validation is possible. Metrics like mean-squared error for regression trees or misclassification rate for classification can be measured after each tree the B. The biases from individual smaller subsample trees are often eliminated by taking the majority vote or average across the entire forest. Random forests have several peaceful advantages. Their computation time is quite efficient. Overfitting is not a problem because the ensemble approach makes the model robust. Classification accuracy is very high. They are robust against non-relevant descriptors, so you don't necessarily need to pre-process and remove them. Random forests work well if a B is high enough, creating a large, diverse forest. They can be used on X blocks where K is greater than N and on highly nonlinear datasets. They are particularly good when an appropriate preprocessing nonlinear transformation is unknown. If you're trying to predict a categorical variable, implementing continuous models like regression trees, random forests, or ANDs would be better than latent variable methods. They can identify trends, reduce errors, and offer better optimization outcomes. Let's gently summarize our methods. Linear regression, simple, interpretable, fast, works with uncorrelated data. Assumes linearity, poor with collinearity or nonlinear relationships. Predicts continuous outcomes. K-means clustering, unsupervised, identifies hidden patterns, fast on small data. Requires presetting K, assumes spherical clusters. Discovers groupings when class labels are unknown. PCA, reduces dimensionality, removes collinearity, good for visualization. Doesn't consider Y, unsupervised, hard to interpret components. Preprocessing or visualizing correlated X variables. PCR combines PCA plus regression, handles collinearity in X, ignores Y when choosing components, may drop predictive info. Models multiple uncorrelated Y from correlated X. PLS reduces X and Y jointly, handles multicollinearity in both. Can overfit with too many components, less interpretable. When X and Y are both highly correlated. ANN captures complex, nonlinear patterns, scalable. Requires lots of data, prone to overfitting, hard to interpret. Models huge, nonlinear X and Y with unknown model. Random forests handles nonlinearity, built-in feature importance, works with mixed data. Can be slow on large data, less interpretable than single trees. Similar to ANN but with better interpretability. Classification trees, simple, interpretable, handles nonlinear splits. Instability, prone to overfitting without pruning. Binary classification with simple rules. KNN, simple, no training time, effective in homogeneous feature spaces. Slow at prediction time, sensitive to irrelevant features. Binary classification when data is tightly clustered. As our tranquil journey through the world of big data comes to a gentle close, allow these concepts to softly settle in your mind. We have explored the serene art of visualizing data, revealing its hidden stories. We have calmly delved into the intricacies of regression, predicting patterns with peaceful precision. We discovered the quiet power of latent variables and principal components, simplifying complexity. We addressed the subtle challenges of outliers and model diagnostics, ensuring reliability. Our path led us through the iterative calm of NIPALS, uncovering the relationships between X and Y. We embraced the elegant learning of artificial neural networks, adjusting weights to find optimal pathways. We then grouped data with the tranquil logic of clustering and made gentle decisions with decision trees and random forests. Feel the peace of understanding wash over you. The vastness of data, once overwhelming, can be gently navigated and understood through these thoughtful methods. Let the rhythm of these ideas guide your breath, deepening your relaxation with each passing moment. Your mind is now filled with new insights, calmly absorbed and ready for integration. Drifting deeper, you are safe, you are calm, and you are ready for a profound and peaceful rest. Good night.